Good morning, my name is Nguyen, and today I'd like to give a teaching demonstrations on a topic in Introduction Machine Learning course. The audience, student audience in this course, I expect to be on the third year or fourth year undergraduate program, so we can expect them to have a few semesters of programming already, knowledge on data structures, and a few lectures in the machine learning course. And the topic we'd like to cover today is called adaptive boosting, which is an ensemble method to combine simple rule into a more complex classifiers. So for some of the learning outcome that we like to accomplish today, we like to have be able to tell machine to be recognized from real apple, from plastic apple. We're going to try to understand how adaptive boosting works. And finally, we hope to demonstrate in Python on some toy data set. So our task is recognizing apple. So first thing we do, we collect a set of real apple, and you can see here, and a set of plastic apple, you can see here. So each of them having different characteristic, and you can observe some rule to tell them apart based on some of their characteristic. So my question to you guys is, can you think of some simple rule that can separate the real apple from the plastic apples?
Well, I think one way we can look at the redness. You know, the real apple will have more redness than the plastic one.
Okay, so redness is a good way to go. That based on color. So you say the rule, if you have past a certain redness, you're gonna consider that real apple. If not, fake apple. So that's very good observation. Is there any other way you can tell the difference between these two classes?
We can look at their shape. You know.
Okay, that is great. That is great. So you can see that the plastic apple seem to have a more similar, say, consistent shape compared to the real apple. So that's a good indicator to tell them apart. How about weight? Can you tell the difference based on the weight of the real apple versus the plastic apple?
Yeah, I think the real apple will weight more than the plastic one. Plastic one definitely will be light.
Right. So these is just, you know, some observation that human can use, and none of them are perfect. Some of them, you know, is general rule of thumbs. So we're gonna utilize some of these rules that you just told me to build a better system to recognize apple. So we're gonna base on some boosting strategy. The first strategy we have, you're gonna have many rules like you described based on shape, color, weight, and to have them vote on the decisions. And the way we're gonna select rule, we're gonna select rule sequentially, and we want the later rule to correct the mistake that the previous rule made. We also gonna be smart about giving more importance to the rule that are more accurate than the others. And finally, we're gonna try to build a complex rule by combining all of our rule votes. So let's plot this apple into in terms of their color. So you can plot from not red to red in the color axis, and also on the weight from heavy to light. So assuming depend on the characteristic of each of these apple, you can plot them in this two-dimensional plane. So you can see they kind of be able to tell the different class. But now we have to tell machine how to recognize them using our simple rules. So one thing you can do, you mentioned about the redness of the apple. You can see where it's gonna lie on this axis. So split it into two sides. So maybe your first simple rule would be like this. So they can tell, okay, if you pass a certain redness, I'm gonna call you real apple. If not, you are plastic apple. So that's great. But you notice they're not perfect rule, which is miss this real apple right here. And it's also considered the red plastic apple as real apple. So these are the instance that it needs to correct or focus on, classify correctly. So what it does, what AdaBoost does or adaptive boosting does, is that you're gonna try to make this weight of these sample larger, while other instance of apple that are correctly, you're gonna make it smaller. So the next round, you're gonna try to focus on these. So you can see you're gonna focus on that. So you watch them closely, I'm gonna increase the weight of these instant while decrease the weight of the other. So there. So this weight now is larger, and the next round iteration, we're gonna try to make sure we classify these things correctly. So where do you think, if I wanna correct them based on weight, where do you think my rule should be?
Somewhere in the middle.
Somewhere in the middle, right? So we right there. So we now be able to tell if it heavier weight right down here, real apple, less weight plastic apple. So these two are now classified correctly. So that's great. However, if you notice, these two now incorrectly. So the next round we're gonna think about, I'm gonna increase the weight of these two instances and see if I can find another rule that be able to correct them. So for this one, if you want to make sure this is a real apple, you're gonna have to move your rule up a little bit more, up the north here, and you're gonna adjust the weight first, so that's look bigger, and then you move the rule up into here. So now this one get correct, great. However, again, this one you still haven't been able to correct them yet, so you're gonna have to figure out another rule yet, adjusting the weight, and then find another rule to correct them, and we end up at the fourth rule right here. So this one get corrected, and you know, on that side. So we went through 4 rules on 2 axes right here, and if we let them kind of vote on the decision where they think the real apple are and the fake apples are, you can end up with this kind of reddish region and then the bluish regions. And the way we're gonna combine them until we figured out a decision boundary to be able to separate them. And these are where definitely red region, these are definitely blue region, and then certain regions are kind of mixed. So this is a more complex decision boundary, and which is based on the rule that we have earlier, and we combine them to make a more complex rule. So that's essentially how adaptive boosting works. So we're able now tell the difference between real apple and fake apple. But you may ask, well, how I'm doing this in a more algorithmic part, which I describe the essential steps. So the adaptive boosting algorithm called AdaBoost is one of the algorithms that are used to boost the decisions of a simple rule to a more complex rule. And it's proposed by Robert Saperis. So the step is first you're gonna have a training data. So think about this ad, you collect a bunch of plastic and real apple. X is the feature matrix, which is combine all of the color, weight, shape of these apple, and Y is the class of the apple. So whether it's a real, we usually assign +1 for it, or plastic, we assign -1 for it. So we have n number of the training data. And we also assign a uniform weight, so every them kind of the same weight. We don't know which one more important each other, and that's gonna be a weight there. So adaptive boosting run on iteration. So for each T iteration, you're gonna select a base learner or a simple rule. The simple rule signify a hypothesis H, and it's gonna try to figure out what the label of instance X here. And the way it does is gonna try to minimize the errors, the weighted errors, epsilon T, and epsilon is based on the error it make, which is if it predict a different label than the actual label that provided, you're gonna have a weighted error, and you sum them all the instant error to find a number. This is the error of the base learner. So based on this error, we're gonna calculate the importance of this base learner. So if it have high errors, I'm gonna put less important to it. If it had low error, I wanna put bigger important to it. So the weight of the learner. And we can use half of the log of the odds. So the 1 minus the error divided by the error, that's the odd. Basically what it does here, it just scale the error down to numbers here. And assuming the Bayes classifier is good enough to make more than 50% accuracy, this alpha is going to be a positive number. And finally, we try to re-weight all our samples. And the way we do it, we base on the decision that the base learner make and the actual label. So you think about the product of these two things. If they are correct classified, which means the label of the predicted label and the actual label are the same. So their product will be a positive number. So you say, if I'm labeled at +1 and my actual label also +1, that end up to be +1. Or if I predict a plastic apple or -1, and it is indeed -1, it still end up with a positive number. So this one's positive, The alpha we talked about earlier also positive. So the whole thing right here with the negative sign in front of it is going to be a negative numbers. So what happened when you exponent to a negative number, you end up making it a smaller number because correctly it make it smaller. So your weight will be smaller. Now what if you incorrectly classify? So what happened is your sign gonna be a different than the actual label. So you're gonna have a negative number right here, and then when you time a positive number with a negative sign, you end up with a positive number. So when you exponent a positive number, you increase the weight, and that can be done dynamically each iteration. So when you go back to get this, now the next iteration, the base learner gonna try to minimize the error based on these weights. You see the weight W is here. So we iteratively trying to focus on classify the sample that are incorrectly classified on the previous iteration. And that's how adaptive boosting go on and on and on. And eventually after T iteration, it's gonna have the voting decision based on the weighted of the learners, and you sum them all up to make a final decision. And usually because the classify is rather negative less than 1 or greater than 1, you use the sign function to design the label. So that's essentially how adaptive boosting works. So next we're gonna try to dive deeper into the code to see how we can use adaptive boosting on a toy data set. And with that, I'm gonna have a demo in Python. So I'm gonna go to Pythons now. Okay, take a way to exit the presentation first. Okay. And I'm gonna type Jupyter Notebook to demonstrate the code here. And I already write a some code here for the purpose demonstration. So we're gonna try to go through them and explain how the code works. So first is some of the setup code. This is just basically import some module and set up some plot function for some of our pretty figure. So we have that. And then next we have our data set. And our toy data set, we're going to use the moon data set. So basically what you have is the two crescent of a moon. So let me show you here. So it looks like a two crescent of the moon, and you can imagine this is two class. So you have real apple here and fake apple there. And you basically actually can adjust the noise or how much overlap you want this data set to be. So if I increase the noise here, we have a noise parameters. So I want to make it to 35%. It's gonna look a bit more messy, and this will determine the difficulty of your data set sometimes you have to deal with. So at any good practice of machine learning, we're gonna split it into a training set and also a test set. And so you divide your data set into a training set and the test set. Okay. So next we will looking at the base learner. We're gonna use the decision tree for that. And so in order to use it, you import from Scikit-Learn tree module, decision tree classifier. And you can define it at a one split tree. Remember the split that we make along the x-axis and the y-axis? We're gonna specify at the math depth of 1. And then you're gonna train the base learner and you use the fit function. Any classifier, you can use the fit function to train and feeding the training data with this label. After training, you then predict what the label of they gonna make. So you use the predict function for that. And then you trying to figure out how good is your classifier by calling the accuracy score. Basically measure the score of your classifier. So and then go down here, you plot out your decision boundary. So let me run this, and here is what it has. It shows the accuracy of the classifier about 75.6%. And it's also visualize where the decision boundary is gonna be. And it's right here. A bit of messy data set, so that's why it's it's a lower accuracy. Actually, if I go up here and I change to a somewhat lower noise, a bit nicer here, so for the purpose of demonstration, I can run it again to show you the accuracy get a slightly a bit better. But you see that even though it classified many of them correctly, there is a region here that get incorrect classified. So that so now go to adaptive boosting. So AdaBoost in the Scikit-Learn is part of the ensemble modules, and you can import AdaBoost classifiers. You can define AdaBoost classifier using a Bayes classifier, which is the decision tree classifier that we saw above. And also that one extra parameter you have to define is the number of iteration, or how many Bayes learner you want to use. So here, because we have a two-dimensional data set, it's quite simple. We're going to use 10 classifier, but you can tune the how many classified based on the application that you have. And then similarly at above, we're going to use the fit function to train the classifier and predict function to predict its label. And then they print out the accuracy, right? So let me run this code and see how it does. So here we go. So the accuracy of the adaptive boosting classifier is about 98.8%. So it seems it had boosted the performance of the tree classifier using combination of them. And you see, if you visualize the decision boundary, it carves out the decision boundary quite nicely. So this code, you can actually try it for yourself. I'm going to provide you this code later on, and you can set up some experiment, maybe compare different performance, depends on the noise level. That's it. You can actually load up other data set if you want to and see how it works. But hopefully that sort of give you a chance to test AdaBoost and explain how it behave a certain way. So that's maybe part of your homework that you would do. Now let's get back to our presentation here. And some question may arise is why we use boosting? Okay, so there's several reasons that boosting has some advantages. So number one, it is fast. So I can just demonstrate to you that boost run very fast, it train fast, and it tests fast. If you have to implement, it's pretty simple to implement as well. To follow the formulation that in the algorithms. And this have little parameter to tune compared to other machine learning technique. The only parameter you need to tune is the number of iteration t, and you can just set up as just a number. It doesn't need prior knowledge on a Bayes classifier, so it doesn't need to know what it is. It's going to use the result from that Bayes classifier. And so it's very flexible to combine with another learning algorithm. So you can combine support vector machine on adaptive boosting classifier, or you can have decision tree or naive Bayes classifier combined with adaptive boosting. And one application that boosting have been shown to be very successful is the phase detection, and that proposed by Viola-Jones phase detector. And the Viola-Jones phase detector actually been used in the early version of the image API from Apple. So you can see if the phase detection application, you kind of recognize the face here. But what it does is actually it crop out a lot of images around here, image patch. And it determines whether it's a real face or not a face. So just think about it, it's real apple or fake plastic apple. And if it knows if that's the face, it would put it on the screen so you can recognize the face. And the simple rule that it actually used to recognize these faces are these simple rule. And it's based on very simple observation on the human face is that so they use a two band, a dark band, and the white band here. And you notice along the eyes, the intensity trying to be lowest, darker region, compared to the region above the cheek, more white region. So this typically give a good response to this filter. Another simple rule it uses is that it uses the three band, dark, white, dark here, and you notice the region of the eyes are dark, and then along the nose are brighter region, and then darker region. So this one also have a good response. And so using AdaBoost combine all these features to make a stronger decision on the face detection. So for the learning outcome today, we have shown a way to teach machine how to recognize real apple from plastic apple. we now understand how adaptive boosting works, and we actually be able to demonstrate adaptive boosting on a toy data set. So that all the lectures today, and I will be happy to take in any questions.